Section 31.5 Rotational partition function of diatomic molecules and linear polyatomic molecules. For the two-dimensional rotation of a linear molecule, such as H2, HCl, and HCN, the rotational energy is equal to J times J plus 1 times h bar squared over 2I. H bar is the reduced Planck constant. I is the moment of inertia. J is the rotational quantum number. J can be 0, 1, 2, 3, 4, etc. For a diatomic molecule, the moment of inertia is equal to mu r0 squared, where 1 over mu is equal to 1 over m1 plus 1 over m2. R0 is the bond distance. For a linear polyatomic molecule, the moment of inertia is the sum of m sub I times r sub I squared. R sub I is the distance between the mass m sub I and the center of mass of the molecule. You can use this equation to derive the moment of inertia for a diatomic molecule as well. The rotational partition function of a linear molecule is this: the sum of 2j plus 1 times e to the power of negative. This is rotation energy over kBt. Why 2j plus 1? This is the degeneracy of the jth rotational energy level. This is because m sub j, the z component of j, can adopt 2j plus 1 different values. This z component, m sub j, can be negative j plus 1, etc., to 0, etc., all the way to j. So there are 2j plus 1 possible values here. So how do we evaluate this sum? We can make approximations by replacing this sum sign with an integral sign. So we'll just integrate this. And how do we integrate this? We'll do variable substitution by setting x to be j squared plus j. And then dx is simply 2j plus 1 times dj. Therefore, we have this 2j plus 1 times dj is equal to dx. And over here, j times j plus 1 is x. Therefore, the rotational partition function of a linear molecule is approximately this. And this is a simple exponential function. We can further set z to be this constant times x, and therefore x is equal to 2I kBt over h bar squared times z. And then we get this equation. The rotational partition function of a linear molecule is 2I kBt over h bar squared times this integral. The value of this integral is simply 1. Therefore, the rotational partition function of a linear molecule is 2I kBt over h bar squared. But very often, we write this linear rotational partition function in this form, kBt over hcb. So hcb is equal to h bar squared over 2I. And this b is just defined this way. B is called the rotational constant. The expression of B is this. We move this hc to the right-hand side. So B is h bar squared over 2I hc. The reduced Planck constant h bar is h over 2 pi. So we can further simplify this to h over 8 pi squared times c times I. What's the unit of B? The unit of B is meter to the power of negative 1, or more commonly used, centimeter to the power of negative 1. We did not take the symmetry of the molecule into account when we write this partition function. After the symmetry of the molecule is taken into account, we have to divide this rotational partition function by sigma. Over here, sigma is the symmetry number. For example, when we study the homonuclear diatomic molecule or any other linear molecules that belong to the d infinite H-point group, we must account for the fact that a rotation by 180 degrees interchanges two equivalent nuclei of this homonuclear diatomic molecule. Because the new orientation is indistinguishable from the original one. After the rotation of this homonuclear diatomic molecule or any other linear molecule that belong to this d infinite H-point group, we have to divide this partition function by 2 so that indistinguishable orientations are counted only once correctly. If you have a heteronuclear diatomic molecule or any other linear molecules that belong to the C infinity V point group, a rotation by 180 degrees produces a distinguishable orientation. So there's no reason to introduce any symmetry number here. The symmetry correction is unnecessary. Or if you look at this equation, this sigma is simply 1 for a linear molecule with a C infinite V point group. Section 31.6, Rotational Partition Function of Nonlinear Polyatomic Molecules. So first, let's review the rotational partition function of a linear molecule. It's kBt over sigma HCB. So the more important part is kBt over HCB. You see this kBt over HCB1, kBt over HCB2, and kBt over HCB3 here. Each term is raised to the power of 1/2. All right? B1, B2, B3 are the 3 different rotational constants regarding the rotation about the x, y, and z directions. And over here you have a square root of pi on top and then the symmetry number on the bottom. The symmetry number can be determined if you know the point group of the molecule. For the C1, Ci, Cs, C infinite V point group, sigma is 1. For Cn, Cnv, Cnh point groups, sigma is n. For the D infinite H point group, sigma is 2. For the Dn, Dnh, Dnd point groups, sigma is 2n. For the S2n point group, sigma is n. For the T and Td point groups, sigma is 12. For the molecules with a OH point group, sigma is 24. For a molecule with this IH point group, such as bucketball, sigma is 60. Again, this sigma is so-called symmetry number. This is to take the indistinguishable orientations of the molecule after the rotation into account. So again, here's a simple example. If you have a homonuclear diatomic molecule and then you rotate this molecule 180 degrees, there's no difference before and after the rotation. Over here, similarly, when you have a water molecule, after you rotate this molecule about the principal axis 180 degrees, you cannot tell the difference. Therefore, sigma is 2. Ammonia, sigma is 3. Methane, sigma is 12. Again, for methane, you can rotate this molecule 12 different ways, and they are all indistinguishable from each other.